is the VAE, okay? So, autoencoders, autoencoders. So this is, as I said, the goal is, it's unsupervised learning for low distribution feature representation from this unlabeled training data. So again, we are trying to get this Z, okay? Usually this Z, this latent dimension, is a much lower dimension compared to X. And this is very useful for, dimension reduction, right? So in this sense, you can learn meaningful features that can, capture what data is about, right? This is, replacing or enhancing the, labor-intensive feature engineering, right? Okay, so we have an encoder that goes from the input X to the hidden features like, or the hidden labels, hidden vectors. Let's call it a Z, okay? This is called encoder. We have already learned it before in the encoder-decoder, right? Remember, if X is image, the encoder is a CNN, and then the feature is just the hidden labels, hidden vectors, right? Okay, hidden variables, right? So originally, people can start with just a linear and then nonlinear, like MLP kind of thing. But later on, you can use deep, fully connected, or ReLU, or CNN. So that's autoencoders. First of all, the encoders part, right? But the question is, how do you learn this Z, right? How do you learn this, process going from X to Z, right? Well, the idea is called auto-encoding. So it's like auto. By auto, you mean that, it's doing something to itself, right? So in the sense that you start with the input X, and then encoder will generate the hidden variables or the features Z, and then you take those Z and feed them to a decoder, right? And this decoder will generate the reconstructed input data X hat, and you want this X and X hat to be as close as possible, right? So we have learned this before as well, actually, the encoder-decoder architecture, right? Back then, we talked about different choices, right, of the blocks, and even in the language models, how we pre-train them. Okay, so this is one example, right? So you have the input data, and then the decoder, let's talk about encoder first, is a 4-layer convolution, right? And then the decoder is a 4-layer up convolution, right? So it's like one is going, here is like a dimension is going down, and then this dimension is going up, is like a unit, right? So this is what autoencoders look like, right? Is encoder, decoder. Okay, and then the loss here is very simple. The distance or the difference between the input and the actual data and the reconstructed data. So the input and the output, right? So here you see that there's only X, there's no Y. There's no Y, right? Right? So in this sense, there's no labels, right? It's unsupervised learning, okay? After you're done, right, you can throw away the decoder and then you just use the encoder, right? Right? So, and then you can feed these encoders output to some predictions or classifiers, right? And then you can fine-tune this encoder jointly with the classifier. We have learned this pre-training before, right? Because in this sense, this part is already pre-trained, right? And then when you do the supervised learning, right, you will have a new loss, right? And then some of the parameters are already initialized and some are not, right? We have learned in the previous lectures that we can even make those layers as much pre-trained as possible if we choose the pre-training tasks properly, right? Remember that. Okay. Now, this autoencoders, right? So this is autoencoder, AE, right? They can reconstruct data and learn features to initialize the supervised model. And then the features are low-dimensional representation of what is the training data, right? And then the question is the following. Can we generate new images from an autoencoder? Can we? If you want to generate a new image, you have to use a decoder, right? Can you generate a new image from autoencoder? Sorry, I didn't notice that. What? You don't think so? Why? Right. So thank you, Do-Young. So the answer is no, and because the model is just trying to reconstruct the sampled data, right? The images that have been seen before. If I want to generate a new image, it sounds like I have to change Z somehow from those already learned, transformed from X sub I, right? But I don't know exactly how to do that. I don't know how I perturb Z and I get a new image, right? So that's why you need to somehow spin it. You have to somehow get a probability distribution of the Z. You see what I mean? Don't treat it as, a variable. Treat it as a random variable, okay? If you put that spin, probabilistic spin, on this autoencoder, that's called a variational autoencoder. And then you can generate data from model. You see what I mean? Now keep in mind, Z is no longer a deterministic transformation from X. It has to follow some distribution, so it's a random variable now, okay? So let's talk about variational autoencoders, okay? So the hope is that we can sample from the model and then generate data, right? So let's start. Let's say, assume the training data, xi, right, where I goes from 1 to n, is sampled from the underlying distribution z, right? So d is what so let's say theta is a model parameter, right? And the theta star is a trained optimal model parameters, maybe through these initial autoregressive losses, right? Like this one, okay? I have to train my theta for the encoder decoder. Okay, so given the theta star, the probability distribution of z, right? If I know that, right, this is called the prior, right, of z, and I can sample from the prior, right, get a sample, then feed the sample to the decoder, right, and then I get the true conditional distribution of P of X given Z, right? Because that's what decoder does. You feed an input of Z, you get an output of X, right? So I'm basically, getting a sample from the true conditional distribution, right? So this is what the idea is about. So this is the intuition, right? Like X is the image, Z is the latent vectors used to generate X, like attributes, orientation, but of course you know that this latent variable is way deeper than the attributes or orientation and so on, right? It's a latent hidden variable, right? Okay, so as I said, this theta star is the optimal. Well, let's say this is the true parameters that we want to estimate. Let's say theta star is the true parameters, and then maybe we want to use a theta hat to denote the optimal hyperparameters that we estimate, right, or estimated. Right? So how do we represent this model, right? So first you want this P of Z, right, because you want to fit your model distribution to ideal distribution. So you may want to make this prior P of Z to be as simple as possible, right, like Gaussian, which only has mean and covariance matrices, or maybe even this is even independent dimensions. Then your covariance is just diagonal, right? But your conditional P of x given z, the decoder network, can be complex, right? This can be much more complex. Your P of z, the source can be simple, but when you project it to the image world or to the data world, this can be complicated, right? So P of z is simple, but P of x given z is complex, and we can do that using a neural network, okay? So this is the idea. And then we want to train the model, right? How do we train the model, right? So the strategy here is that we can maximize the likelihood of the training data, for instance, right? If you look at what this one is, this is P of theta given P theta of z times P of P theta of x given z, which is basically what? P theta of x and z, right? Right? And then I have a prior distribution of the z, right? So I have the joint distribution, right? And I do the integral. What is this? What is this? We have seen this before. Let me remind where it is. Just right here, right? Right? Okay, so okay. Do you see a problem of this? You know, if I try to maximize this likelihood, which needs to be calculated in this way, what is the problem? Do you see a problem? Is it easy to maximize this likelihood? Huh? X given, the second one is complex, right? And what challenge does it bring? So, I think you're heading the right direction, but I want to explain it clearer that in fact, some of these terms or this, calculation can be intractable. That's the challenge. I will explain what do I mean by saying it's intractable. So this likelihood is what I said in the last slide, right? And the first one is simply sampling the Gaussian prior, right? The second one is the decoder neural network, right? The problem is that, you have to compute P of x given z for every z. You have to do this integral. You see what I mean? You have to do this integral. And this integration is kind of difficult. Okay? And it's intractable to compute every decoder output for a given, z, right? The input to the decoder or the hidden. So, the posterior density is also intractable, right? So z of x, we can rewrite it using, the base theorem. And that's what we have. And that's also intractable, unfortunately, okay? So getting this data likelihood is, intractable. And in this case, as I said, this also, eventually affects your posterior density as well, right? What do we do? What is the solution then? Okay, the solution is that, we already used a neural network called a decoder to model P of x given z, right? But what we want to do further is that, this P of z given x is intractable, right? What is P of z given x? You have seen that before. Right? I can get another neural network. This time, you know what it's called? It's called encoder neural network, right? Whose parameters are phi. And I try to approximate p theta z of given x. Okay, I try to approximate it. So we will not be able to, optimize the likelihood still, but we can find the lower bound of the likelihood. And then we can, it's called elbow, it's abbreviation. We can optimize the elbow or the lower bound of the likelihood using this solution. Okay? Let me try to give you the answer here. So again, we are having encoder and decoder networks, right? And they are probabilistic, right? So we have encoder network. Let's remember that we started with a decoder network, which is complex, and the P of Z is simple, right? And the decoder network basically has a mean and the covariance, right? So that's how we can sample from this probabilistic distribution. Then we additionally had to introduce the encoder network parameterized by phi, okay? And now let's talk about this, maximization or optimization, because we are trying to train these model parameters C and theta and phi, right? So we are trying to again maximize this log likelihood, right? Let's try to recalculate the data likelihood for each data I, right? Now this probability log of the p can be calculated by simply by this expectation, right? Right? So we are taking expectation with regard to z, where z is the sample from what? The encoder, parameterized by phi, right? Right? And then here, the quantity to be averaged or taking expected is not dependent on z, it's just p of xi, given theta, right? Now, we can use the base rule, right? And rewrite p theta, right? Rewrite p theta. And then in the numerator and denominator, we can multiply both by this q phi z given xi, right? Then what you get is the following. You can take the log of the product into the sum of two logs, right, in three terms. Right? The first term is log p of xi given z, right? That's the first one. The second one is, log q divided by p, right? That's q divided by p, right? The first one is this term. Second one is q divided by p. And, I'm sorry, q minus q divided by p. So it's this two, okay? This two. And the last term is log q divided by p for this one, right? So this is the ratio between these two that we are looking at. Okay, we are taking the log. And then, we can figure out that actually this is the KL divergence, actually. This is the KL divergence of the two distributions. And this is the KL divergence of two distributions, right? Right? And then we can, take expectations. These expectations basically give us the KL divergence. And then let's look at these three terms. Again, right, the first term is x given z, though that is a decoder, right, with the parameter theta, right? So, we can estimate this one by sampling, basically, right? We can just take the samples from the decoder, right, and estimate this expectation, right, by sampling, right? So the second one is the KL divergence between this Q. What is Q? Q is x to z. So that is an encoder network, right? And PZ. What is PZ? PZ is just Gaussian, remember? So it's actually very easy, and there's a closed form solution to get the KL divergence between the Gaussian and these, encoder modeled distributions, okay? And the trouble comes from the last term. This is the KL between the two, and the problem is that we know getting this P of Z given X is intractable. So it's not like rewriting this, the bound would make things tractable. No, it's still not tractable. It's still intractable because of this, all right? But this is only one of the three terms that is intractable. And you know that KL divergence is lower bounded by 0. So you can say that the whole log likelihood is bigger than or equal to the first two terms plus 0. Okay, that's the lower bound. So you can still not, optimize the likelihood directly, but you can optimize the lower bound, which is the sum of the first two terms. Okay, and that is very tractable. Okay, this is also called elbow. Right, this is a variation lower bound called elbow. So instead of maximizing the log likelihood, we can maximize the lower bound instead. Okay, then we can get the optimal parameters for the encoder and the decoder. Okay? And then let's finalize and put things together, right? So what we are doing is that we have this input data X, right? We have to, this is going through the encoder network, right? Which is some kind of distribution with mean and standard deviation, right? Then we sample Z from this model distribution and then feed to the decoder network. These two networks are parameterized by phi and theta respectively. In the end, we reconstruct X hat, right? And to train theta and phi, we need to maximize the elbow or the lower bound of the likelihood, right? And then, we know how to forward propagate, and then we can calculate gradient backward, so we know how to do this, okay? All right, I think I would stop here, right? So variational autoencoders, we talked about what's the idea and how to train it, right?